So question 2 is about Dijkstra's algorithm, or Dijkstra's algorithm, whatever way you want to say it.
Dijkstra.
You can read the question yourself, but basically what you want to do is you need to find Dijkstra's algorithm to find the route between x and y that is the cheapest to improve. So you're trying to find the shortest path from x to y, because each of the numbers represent the cost of improving that path. And then calculate the cost of carrying out these improvements. So you need to find the shortest route and the cost of repairing the paths along that route. So I know a lot of people, when they're doing Dijkstra's algorithm, they use boxes, or I think it's called Dijkstra's key or Dijkstra's key, but I'm gonna do it this way because it's quicker, and I think you're allowed to do it because it says at the top of the exam that the provided graphs and the networks and stuff, they will be scanned and show all your work on either the answer space or the graphs and networks. So I think you're allowed to draw on it. Again, we're not sure, no marking scheme, but that's what I'm going to do because it's a lot quicker, and again, time is a big thing in the exam. So we're starting at x, so I'm going to show the way that I learned to do Dijkstra's algorithm. So we put a box around x, because that's where we're starting, and then we look at everything that x connects to, and we put a box around them as well. And actually we color in x as well, because that one's already done. We don't need to do anything to that, because that's the starting point, so we color it in to say it's done. Now for C, the fastest way to get from C, or the way to get from C to X, that's going to be 1,250, and then just write down that that's going to X. Then here we have 3,400, that's also going to X, and then we have 2,500, also going to X. So now we see which one of these is the smallest. Well, it's 1,250, so we color that one in, put an arrow pointing towards X, and put a circle around it to show that's the value we're using. Now we repeat the same thing. So we look at everything that C is connected to. Well, X is already complete, so we don't have to worry about that. But we look at B and F, so I'll put a box around F. Now to get from F to C, we have 3,900 plus the 1,250 to get back to X. So we have to add those together. We get 5,150. And that's going to C. And then for this B, we're going to have 900 plus 1,250. That's 2,150. And that's going to C. So now we do the same thing. We look at all the empty boxes and we say which one's the smallest. Well, B is the smallest with the 2,150 C. That kind of looks like an L there. So now we color in the B and we put an arrow down to C. Now we look at everything that B is connected to. So B is connected to F and G, so we can put a box around G. Now we have 4,200 plus the 2,150, and that'll give us 6,350 to go to X via B. So we write down B, show that's going via B. And then now down at F, we have 2,150 plus 2,150 is 4,300, and that's going via B. So now we have a look which one's the smallest. Well, up here at A is the smallest, so we color that in, draw a little arrow, and then we look at the ones that are connected to A. It's E and D. So now we have that 3,400 plus 800 will give us 4,200 to go to E via A. So that's going to write down A, so that's going via A. And then we have 2,650 plus 3,400 gives a total of 6,050 going from D to the starting point via A. We write down A, so that's going through A. Then we see which one's the smallest. Well, it is the E, so we color in the E, draw a little arrow, and put a circle around this. The one it's connected to is D, so we can say 4,200 plus 1,750. That'll give us 5,950, and that is via E. Now we have a look at all of our empty boxes. Which one's the smallest? It's F down here, with that 4,300 going up to B, so we draw an arrow to B, put a circle around it, look at the things beside it, put a box around H, put a box around I. Now for H, we're going to have 1,600 plus 4,300, which is 5,900. And remember, this is via F. And then for I, we have 4,300 plus 2,200, which is 6,500. And that again is via F. Now we look at all of our partially complete, the ones with the boxes around them, and we look which one's the smallest. Well, it's 5,900 here, so we color that in the H, and it's going to F, so we draw an arrow to F, and then we look at the ones beside H, so we have I, and we have G. So to go to G, we have 5,900 plus 1,350. That'll give us, I'll just write it under 7,250, and that's via H. And for I, we have 5,900 plus 1,800. So that's a total of 7,700. I'll just write it down here. And that's via H. Now we look which one's the smallest. So we have 5,950 up here at D. So we color that in. And remember, that's going to E. So we draw an arrow down to E. Put a circle around that. I guess the circle is only important when you have two values to show which one of those two you're using. But I'll put them on all of them just in case. Now connecting to D, we have J. And we also have G. So get from D to G, we have 5,950 plus the 650 is 6,600, which I'll write here to the side. And that's via D. And now to go to J, we have 5,950 plus 3,000 is 8,950, and that is via D. Now we look at these, which one's the smallest? Well, 6,350 is the smallest, and that's going to B, so we color in G, draw an arrow down to B, circle the value we're going to use. And now what's connecting to G? Well, it's just K. The rest of them are already complete. Now to get from G to K, it's 6,350 plus 2,500. That's 8,850, and that's via G. Now we look at all of these values and we see which one's the smallest. Well, it's I. So we color it in, and we're going to F. So we draw an arrow there, circle the F to show that we're using the F. This is going to go to L and K. So to go from L, we have 6,500 plus 4,750, which is 11,250, and that's going to I. And to go to K, we have 6,500 plus 2,350, which is 8,850, and that's going through I. Now we look which value is the smallest. Well, it's K. They're both 8,850, so we can actually go either way, I or G, so we can draw both arrows to show that. And I'll just circle this one, just to keep it consistent. Now K is connecting to L, J, and M. So to go to J, we have 8,850 plus 1,900 is 10,750, and that's coming from K. Now to go to M, we have 8,850 plus 2,400 is 11,250, and that's going through K. And then finally I, to go from 8,850 and then plus 950 is 9,800, and that's going through K. So now which one of these is the smallest? Well, it's 8,950. So we color in the J, draw an arrow down to D, circle the value we're using. Now what's connecting to this? It's just M. So you have 8,950 plus 950. That'll give us 9,900. And that's going through J. So 9,900 going through J. You see which one's the smallest? Well, it's the 9,800 down here at L. And that goes up to K. So now we box the ones that it's connected to. So for N, we have, and circle the value we're using, which is 9,800. So now 9,800 plus 1,950 is 11,750, and that's going through L. And for Y, we have 9,800 plus 2,300 is 12,100. That's going through L. Which one's the smallest? Well, M is the smallest. With 9,900 going through J, so we color in M. Draw an arrow up to J, which is this one. And now the only one that M is connected to, that's not done yet, is Y. So we circle that 9,900. And so we have 9,900 plus 1,550. That's going to be 11,450. That's going through M. Which one's the smallest? It's N. So we color in N and draw it over to L. And now N is connected to Y, so we can say we're using 11,750. That's the value we're using for N. And again, from N to Y, we're adding the 1,800, giving us 13,550. And that's through N. So now we're finally at our final point, so we choose the smallest one, which is 11,450 through M. Then we color in Y. And we put an arrow up to M. So now we have this very messy diagram, but now we can use that to answer the question. So to find the route between X and Y that's the cheapest, we follow these arrows. So I'll draw it in green. So if we start at Y, we can follow an arrow. The only arrow coming out of Y goes to M. So we go over to M. And then now the only arrow goes over to, what's this? J? Yeah. Then the only arrow coming from J goes over to D. and then the only arrow going from D goes down to E. The only arrow going from E goes up to A. Well, the only arrow coming from A is from A to X. So we can write that down. We can write X, A, E, D, J, M, and Y. That's the shortest path. So now for the cost, I don't know if you'd have to show your workings out because we actually found the cost. It's here. The value we got for M, 11,450. And the way we got that is we were adding up the values all the way over. So we started off by adding the value from A to X, and then we added on the value from A to E on top of that, and we did so on. So it's 11,000 euros and 450. If you want, you could add them all up, but I don't think you'd have to. I think if you indicate on the diagram that this is the cost, that'll be okay. So then part B was a collisions question, and sometimes collisions questions can be a little bit dodgy, but this one was actually all right. So there's a lot of information, so let's just go through it slowly. So two smooth spheres, and smooth is important because it means no friction, although I don't think they've ever put friction in a collisions question. Equal radius, I don't think that really matters. I think that's just saying that you don't need to worry about the size of the spheres when you're calculating when they're going to collide and stuff. And their mass of m and 2m, so that's also important, because the conservation of momentum, the principle of conservation of momentum, you need to know what the masses are. They collide obliquely, which you can see in the diagram. They're not like directly colliding. One of them is moving at an angle. That's what that means. The line joining their centers at the point of impact lies along the I-axis. That's important because it means that when the collision's actually happening, the only thing that's changing is stuff in the I direction. Nothing in the J direction is changing, because when they collide, the point that joins their centers, the point of impact, is along the horizontal axis, which means that the only things that are going to be changing are along the horizontal axis. If you don't know what that means, you'll see it later on. Before this collision, sphere P has a velocity of 4 at an angle alpha, where sine of alpha is 4/5. So that's a nice 3, 4, 5 triangle. And before the collision, sphere Q moves with a velocity of 3.2 meters per second. That's perpendicular to the y-axis. So that means it's only moving up. Now we need the velocity of each sphere. So usually what I'll do is I'll draw a little table. So let's have a look. So for Q, well, we know it's 3.2 meters per second and it's perpendicular to the y-axis. So that means it's moving upwards at 3.2 and it's only in the J direction, as you can see in the diagram. Now for P, it's a bit more difficult, but it's nothing too bad. So first of all, let's have a look at this. Sine alpha is 4/5. So you can see in the diagram, they have a little triangle like that. So let's just draw that out. So sine of alpha is 4/5. So sine is opposite over hypotenuse. So that's 4 here, 5 here. You could use Pythagoras' theorem to figure out this side, but it's a 3, 4, 5 triangle. You can just figure out that this is 3. Also, if you prefer, I guess you could technically simplify sine alpha, find out what alpha is as a number, but this is a nicer method because it's a little bit more accurate, I suppose. Because now we can calculate sine, we know what sine alpha is. Cos alpha, well, cos is adjacent over hypotenuse, so that's 3/5. And then tan alpha will be opposite over adjacent, which is 4/3. Although I don't think we need that, but either way, it's there. So now if we think about the velocity, so I'll draw the velocity down here. So we're told that it's going at a velocity of 4 meters per second. So we can resolve this velocity into two directions. So this direction, again, you can do the trigonometry out, but once you do these enough times, you know that this one's going to be 4 cos alpha, and this one's going to be 4 sine alpha. And for cos alpha, well, cos alpha is just 3/5, so 4 times 3 is 12/5. Or you can write it as a decimal if you want, but I usually prefer fractions. And then for 4 sine alpha is 4/5, so that's going to be 16/5, because 4/5 multiplied by 4 is 16/5. So maybe just for my little table, I'll put them in decimal. So 12/5 is 2.4, so we have 2.4 in the I direction, 3.2 in the J direction. And then afterwards, I'm just going to remember the I velocity is the only thing that's going to change. So I'm going to call the I velocity for P lowercase p plus, and then the J will stay the same, 3.2J. And then here we're going to have lowercase qi plus 3.2J. Now you can call them VP and VQ if you want, but that takes a lot longer to write out and you don't need to, so I just call them P and Q, because if there are more variables though, you might want to do that. So normally when you're doing a collisions question, there are three things you'll do, and you'll do them usually in this order. So the first thing you'll do is you'll do the conservation of momentum. So this formula is on page 51 of the Formula and Tables book, but you shouldn't really need to remember it. It's just the momentum before equals the momentum afterwards. And remember, momentum is just mass times velocity. So it's here in the formula book if you need it, but yeah, page 51. So we can just fill in. Remember, the mass of P is m, and the mass of Q is 2m. Just write those here to remember. And when we're applying the conservation of momentum, it's important to say we're doing this in only the x direction, or the I direction rather. Why is that? Well, the velocity before in the j direction, both of them are the same, and the velocity after in the j direction are both the same. The masses obviously don't change, therefore the momentum in the j direction is actually going to be the same before as it is after. So we don't need to worry about that, they're all going to cancel. We just have to look at the conservation of momentum in the I direction. So we can fill in now, the mass of P, is m, as it says up here, and the velocity of P in the I direction is just 2.4, plus the mass of Q is 2m, the velocity of Q in the I direction is 0. That's going to be equal to the mass of P is m, and the final velocity of P we're calling P, plus the mass of Q is 2m, and the final velocity of Q we're calling lowercase q. So all of those m's are going to cancel if we divide everything by m, and we get that 2.4 plus 0 is nothing, equals P plus 2Q. And that's our first important equation. In a collisions question, I'd usually label them. This is the equation 1, because it can get, not in this question necessarily, but in some other collisions questions, they can get very messy. So the next thing you'd always do in a collisions question is look at Newton's experimental law, especially if they're asking it in terms of E, you're going to want to use this law. So it's on the same page as the conservation of momentum, page 51 in the formula and tables. There it is there on the right. V1 minus V2 equals minus E times U1 minus U2. We can rearrange that slightly to give us that minus E equals V1, we're going to call P, minus V2 is Q, all over UP minus UQ. So minus E will be equal to, what's the final velocity of P? Well, we're calling that lowercase p, minus the final velocity of Q, we're just calling Q, all over, the initial velocity of P is 2.4. Remember, this is only in the I direction. We don't have to worry about the j direction. Minus 0, because the initial velocity of Q in the I direction was 0. So then we can rearrange that to say that minus 2.4e will be P minus Q. So now we just need to solve these two equations simultaneously to get, it's an expression, the velocity of each sphere after they collide in terms of E. So we can do that because we have E here and we have P and Q in both. So let's just isolate P in this one. So we could say that P equals Q minus 2.4e, and let's put this into equation 1. So now we have that 2.4 equals, as you can see up here, P, and P is just Q minus 2.4e, then we're just doing plus 2Q. So we can bring the 2.4e to the other side, and Q plus 2Q is 3Q. The 3Q equals 2.4 plus 2.4e. And I guess we could factor that out, so we could say that Q equals, well, 0.8 plus 0.8e, and you could leave it like that, but Q equals, I'd factor it, it's just a bit easier, 1 plus e. So that's the velocity of Q after, and remember, this is only in the I direction, so it says the velocity of each sphere, it doesn't say the I velocity, it says the total velocity. Well, it doesn't say the total velocity, but it just says velocity, so you'd specify that that means the overall velocity. Anyways, we can now solve for P, now that we know what Q is. So P equals Q, which is 0.8 plus 0.8e. I've just left it expanded because you'll see now. And then minus 2.4e. So now P equals 0.8 plus, that's going to be, or actually that's going to be minus 1.6e. Which means that P equals 0.8 times 1 minus 2e. That's our velocity for P in the I direction after the collision. Now let's just find the velocities. So I'm guessing you could write it in any form. So if you wanted, you could write it as the overall velocity by drawing a triangle and saying, well, this is the I direction, this is 0.8 times 1 minus 2e, and this one is 3.2. And then you can find out what the V is here, but then you'd also need to find out this angle here, and I think is just a lot. And since they don't specify what form you put it into, I'd say they won't mind if you put it into INJ form. So I'd do that. I'd say VP equals, so we're going to have 0.8 times 1 minus 2EI plus 3.2J, because remember the J doesn't change. And for Q, we have 0.8 times 1 plus E I plus 3.2J. And that's the answer. That's the velocity written in INJ form. Again, you could write it in terms of an angle and magnitude, but it's just easier if you're going to have to square the 1 minus 2e and all. It's just easier to leave it this way. They don't specify, and I'd say they'd accept both. So yeah, that's it.